I want you to picture a scene for a second.
Okay.
You're standing right on the floor of this high-security manufacturing facility. The air is heavily filtered, the lighting is just stark white, and right in front of you are these workers in heady protective gear.
Sounds intense. What are they making?
They're assembling live grenades.
Oh, wow. Okay.
Yeah, it's literally a munitions factory. So every single motion these people make is intensely calculated. I mean, they're handling high explosives, and you can practically feel the tension in the room.
Right, I'm sure.
It's like they're collectively holding their breath, just terrified of making even one microscopic error that could trigger some horrible chain reaction.
Well, because it's an environment completely defined by the catastrophic consequences of failure. I mean, workers in that situation, they aren't thinking about, optimizing their output or hitting a production quota. They're just thinking entirely about survival.
Exactly. And that psychology, that paralyzing, overriding fear of a catastrophic failure, is actually the key to understanding a totally different crisis that's happening right now all over the world.
It's wild how those connect.
It is the exact reason why we are intentionally shutting off clean, renewable energy on a massive scale.
Which, seems like a huge disconnect on the surface. You wouldn't normally associate the terror of handling high explosives with, say, a wind turbine just spinning peacefully in a valley somewhere.
No, not at all.
Or like a field of solar panels soaking up the sun. But that psychology is the hidden choke point of the entire global energy transition.
It really is.
The bottleneck holding back renewable energy, it isn't a lack of copper wire. It isn't a lack of power generation.
No, it's a lack of physical telemetry.
Yeah.
And it's driven entirely by human fear and, well, legal liability.
Yep.
Okay, let's unpack this. Welcome to the deep dive. Today, we are exploring the phantom grid.
It's a great topic.
We have a really fascinating stack of sources that pull back the curtain on this invisible bottleneck. We're digging into a staff paper from FERC, the Federal Energy Regulatory Commission.
Right, detailing how transmission line ratings actually work in practice.
Exactly. We're also looking at this massive, incredibly detailed study by CIGRE and Lindsay Systems that analyzed over 800,000 data points on sensorless grid algorithms.
That's a staggering amount of data.
Plus, we've got the technological blueprints from Heimdall Power, this company building autonomous grid sensors, and a collection of founder-grade system architecture notes that basically lay out a specific strategy for unlocking what they call phantom grid capacity.
Yeah, and the foundational problem we're analyzing today is that grid operators are routinely ordering wind and solar farms to just stop generating power.
They're literally unplugging them.
Right, they curtail that clean energy because they operate under the assumption that the high-voltage transmission lines carrying that power are already full.
But the reality is, they don't actually know if the lines are full.
No, they don't.
They are guessing. We are throwing away perfectly good, incredibly cheap wind and solar energy based on a highly conservative, worst-case scenario guess.
Which is just nuts when you think about it.
It is. And to understand how to fix the power grid, we have to start by looking at the mechanics of how we measure its capacity in the first place. And frankly, the way we measure it right now feels like something out of the 19th century.
It really does. Because to grasp why we are guessing, we have to look at the underlying physics of electrical transmission.
Okay, lay it on me.
So when electricity flows through a conductor, these are those massive, heavy braided cables you see strung between towers that electrical current encounters resistance.
Right.
And fundamental thermodynamics dictates that electrical resistance generates heat.
Just like the glowing wire inside a toaster.
Precisely the same mechanism, yeah, just on a much, much larger scale. Now, these transmission lines, they're typically made of a steel core for tensile strength.
To hold them up.
Right, and then that's surrounded by braided aluminum to actually carry the current. So as the current increases, the temperature of the wire rises. And when metal heats up, it undergoes thermal expansion. It physically elongates.
It stretches out.
Exactly. And because the wire is fixed at 2 points of transmission towers, that extra length has literally nowhere to go but down. So the wire sags.
And that sagging is the ultimate enemy of the grid, right?
It is the enemy.
Because if a high-voltage line sags too far, it doesn't even need to physically touch the ground to cause a disaster.
Oh, absolutely not. High-voltage electricity can actually arc through the air if it gets too close to a conductive path.
Just jump right through the air.
Right. So if a line sags too close to a tree canopy or a building or even the ground itself, the electricity will jump. And this creates a catastrophic fault.
Which is terrifying.
At best, it trips a breaker and causes a regional blackout. At worst, the arc flash ignites the surrounding vegetation and you get a massive wildfire.
So the stakes are incredibly high. The National Electric Safety Code, the NESC, they have very strict clearance-to-ground standards.
Right, they mandate an absolute minimum distance that a live wire must remain above the ground or surrounding objects.
Violating that clearance is just not an option. So the question becomes, how do the people running the grid make sure that wire never, ever sags too low?
Well, historically, they've managed that risk by using something called a static line rating, or an SLR.
Okay, SLR, this is the baseline method detailed in that FERC staff paper, right?
Exactly. A static line rating is essentially a hard limit on how much electrical current is allowed to flow through a specific transmission line.
Okay.
But here's the critical part. That limit is calculated based on a theoretical worst-case weather scenario.
Because weather is the primary way these lines cool down, right? Like if the wind is blowing, it pulls heat away from the wire.
Convective cooling from the wind is the single most important factor in keeping a transmission line from overheating. But a static line rating doesn't look at the actual wind. No, it assumes the worst. A standard SLR might assume an ambient air temperature of like 104 degrees Fahrenheit or 40 degrees Celsius.
Wow, okay.
It assumes a blazing, completely unshielded midday sun just pouring heat into the wire. And most importantly, it assumes a wind speed of just 2 feet per second.
2 feet per second. That's basically stagnant air.
Right.
That's completely still, suffocatingly hot summer day.
It is the absolute worst meteorological condition you could possibly have for dissipating heat.
So they use that to set the limit.
Yeah. The utility calculates how much power the line can handle under those specific punishing conditions without sagging below the NESC safety limit. And whatever that number is, that becomes the legal maximum capacity for that line every single day.
That is just wild to me. It's like mandating that every single car on the highway can only drive 10 miles per hour, 365 days a year, just in case there happens to be a sudden blinding blizzard.
That's a perfect analogy.
You're permanently crippling the efficiency of the entire system just to guard against a scenario that might only happen 3 days out of the whole year.
It's a massive sacrifice of efficiency for the sake of absolute risk avoidance. Now, to be fair, the industry has recognized how restrictive this is,
Sure.
and they have implemented some slight variations. The FERC paper discusses seasonal ratings, which apply a different static assumption depending on the time of year.
So it changes in the winter.
Right. For example, the winter rating might assume an ambient temperature of 32 degrees Fahrenheit instead of 104 degrees. Because the baseline air is so much colder, the wire naturally stays cooler,
Makes sense.
which allows the operators to push more current through it during the winter months.
But even a seasonal rating is still a static guess.
It is.
It's just a worst-case winter guess instead of a worst-case summer guess. It still assumes zero wind and maximum solar radiation for that time of year.
Exactly, which is why regions with heavy grid congestion, like ERCOT down in Texas or PJM on the East Coast, they've started using something called ambient adjusted ratings, or AARs.
Okay, what are ARs?
This is the most advanced version of the traditional methods. With an AAR, the utility actually looks at the local air temperature forecast for the day.
Oh, okay, so they were looking at the weather.
Just the temperature. If the forecast says it will only be 60 degrees today, they use a pre-calculated mathematical step function to slightly raise the capacity limit of the line for that specific day.
So they might have a capacity limit for 60 degrees, and then another limit for 65 degrees, another for 70, and so on.
Yep.
So they're basically adjusting the speed limit on our metaphorical highway based on the local temperature.
They are adjusting it, yeah, but they are still fundamentally blind to the most critical variable. Ambient adjusted ratings only look at ambient air temperature. They do not account for wind cooling.
Wait, really?
Really? And as we established, perpendicular wind is the primary mechanism that removes heat from a high-voltage conductor. They also don't account for real-time solar irradiance.
Like whether a cloud happens to be blocking the sun over a specific span of wire.
Exactly.
Wait, hold on. If convective cooling from the wind is the biggest factor, why in the world would an ambient adjusted rating completely ignore the wind? Why not just factor in the wind forecast too?
It seems obvious, right? But the reason is that wind is incredibly localized and highly volatile.
Okay.
ambient air temperature is relatively uniform across a region. Like if it's 60 degrees at the airport, it's probably 60 degrees 10 miles away at the transmission tower. But wind is chaotic.
That's true.
A weather station might report a 15-mile-per-hour wind, but a specific valley where the power line dips might be completely shielded from that wind.
Oh, I see.
Utilities ignore the wind in their AAR calculations because they cannot guarantee the wind is actually hitting the entire length of the wire. And in grid operations, if you cannot guarantee a cooling effect, you cannot legally rely on it.
Which brings us back to the core issue. Even with ambient adjusted ratings, we are still leaving a massive amount of physical capacity on the table because we are still just making highly conservative assumptions.
Absolutely are.
The actual physical aluminum wire isn't the bottleneck. The wire could easily carry the power from that wind farm. The bottleneck is the way we measure risk.
And that leads us right into the human element of this crisis. Because if we know mathematically that these static and ambient adjusted ratings are overly conservative, if we know that there is extra room on the wires 95% of the time, why don't the grid operators just raise the limits?
Right. Why don't they just look at a radar map, see a massive storm front moving in with heavy winds, and manually increase the flow of power?
Because if they do that, and they are wrong, the consequences are apocalyptic. And the liability falls entirely on them.
This is where the founder's notes in our source material provide such a brilliant perspective.
It's a great section.
The author describes their experience working as an automation engineer, integrating a 6-axis collaborative robot into a munitions facility. They stood on the floor of that grenade factory we pictured earlier.
Yeah.
They watched the humans handling the explosives. And the revelation the author had wasn't about making the factory faster or more profitable. It was about safety.
Yeah.
The author realized that the workers on that line were not motivated by innovation or efficiency. They were governed by the profound fear of blowing up.
Of course they were.
The automation, the robot, wasn't introduced to replace them so the company could make more money. It was introduced to absorb the physical risk so the humans didn't have to operate in a constant state of terror.
And the author applied that exact same psychological framework to the control rooms of our power grids.
Yes.
Think about a transmission system operator sitting at a dispatch desk. They stare at screens showing the flow of electricity across thousands of miles of high-voltage wire. They technically possess the physical ability to dispatch more power, to route that cheap, clean energy from a wind farm directly into a city.
But the personal risk is too high.
Exactly. Think about the legal and financial reality. If an operator relies on dynamic, changing data, like a weather app, telling them it's windy to push more power through a line, they are making a massive gamble.
A huge gamble.
If that weather app is wrong by even a slight margin, or if the wind dies down unexpectedly for just 20 minutes, that line will rapidly heat up.
It'll start to sag.
It will exceed its thermal limit. It will elongate, sag right into the tree canopy, and ignite a wildfire that could burn down an entire community.
And when the federal investigators and the lawyers show up to sift through the ashes, whose name is on the digital dispatch log authorizing that extra power?
The operators.
It's the operator's name.
The liability falls directly on their shoulders and, by extension, on the utility's executive board. The potential for billions of dollars in damages and even criminal negligence charges, it creates this total institutional paralysis.
I want to really dig into this dynamic because I think it is the hidden force driving this entire problem.
Let's do it.
Let's look at this from two different angles within the utility. Let's do a role play.
Okay, I like that.
If I put my CFO hat on for a second, my priorities are totally different from the person running the control room. As a CFO, I'm looking at our quarterly earnings report. I see that we have a massive wind farm out in the valley. It is spinning, it's generating practically free energy.
Right.
But we aren't selling it. We are actively curtailing it, telling the wind farm to disconnect from the grid because our dispatch logs say the transmission line carrying that power is at 100% capacity based on its static line rating.
And as the CFO, you are looking at the actual weather outside your office window, wondering why you are throwing away all this revenue.
Exactly.
Yeah.
I'm calling down to the operations desk and saying, look, it is a brisk 50 degrees outside, and the wind is howling at 20 miles an hour. That transmission line is being actively cooled by the weather. Why are you limiting our sales based on a formula that assumes it's 100 degrees and completely still? Turn up the limit and let's sell that power.
And if I am the grid operations manager sitting at that desk explaining this to you and the executive board, my response is grounded entirely in survival.
Okay, let's hear it.
I would have to tell the CFO, with all due respect, my mandate is not to maximize your quarterly revenue. My mandate is to ensure the grid does not collapse and that we don't start a wildfire.
Fair enough.
You are asking me to look at a weather forecast and guess exactly how much wind is hitting a specific span of wire 50 miles away over a mountain ridge. What if the wind is swirling? What if it's hitting the valley floor but missing the ridge entirely? If I authorize another 50 megawatts based on your weather app and that wire heats up and causes a catastrophic fault, it is my career, my freedom, and the company's entire existence on the line.
Wow.
I am not trading public safety for your efficiency. The static rating stays. It is the only mathematical way I can guarantee the line will not melt.
That dynamic right there is the crux of the issue. When you frame it like that, you realize the operator isn't being stubborn or anti-renewable energy.
Not at all.
They are acting entirely rationally within a system that penalizes them for taking risks.
Yeah.
Systems run on fear. They prioritize absolute risk avoidance over dynamic efficiency because the human beings running the system are terrified of the liability.
The founder's notes summarize this beautifully. They wrote, "You cannot ask a system to be efficient if you do not first make it safe."
That's a great quote.
We look at grid congestion and we instinctively assume it is an engineering problem. We assume we need to string more copper wire or build more towers. But grid congestion, at its core, is a human psychology problem masked as an engineering problem.
So, if human fear of liability is the bottleneck, and operators quite rightly refuse to trust regional weather forecasts to push the limits, that raises a massive question.
Which is?
We live in an era of incredible computational power. Why can't we just build a better algorithm? If we feed the absolute best hyperlocal weather data, satellite imagery, and thermodynamic models into a supercomputer, wouldn't that software be accurate enough to give the operators the confidence they need?
It is the most logical next step, right? Utilities are desperate for a solution that doesn't involve spending billions of dollars on new infrastructure.
Right, hardware is expensive.
Exactly. So the promise of software buying a digital subscription that magically calculates real-time grid capacity without having to bolt new hardware onto live wires, it is incredibly tempting. But the reality is a resounding failure.
And this is where the CIGR paper by Lindsay Systems comes in. This study absolutely dismantled the idea that software alone can solve this problem.
We have to look closely at the methodology of this study to understand the gravity of its conclusions. Because this was not a small theoretical white paper.
No, it was huge.
This was a massive empirical analysis of over 800,000 discrete data points collected over 13 continuous months.
Over a year of data.
Over a year. And the researchers looked at high-voltage transmission lines across 3 vastly different geographical and meteorological environments: the western United States, the eastern United States, and Europe.
So they are accounting for arid deserts with high solar radiation, humid continental climates with heavy tree canopies, and maritime climates with volatile wind patterns.
Exactly. They wanted to see how software performed across literally every conceivable variable. They were testing a concept called sensorless rating estimates, or SRE.
Okay.
Their methodology was straightforward. They took all the best commercially available weather data, ambient temperature, wind speed, wind direction, solar absorption, and fed it into highly advanced software models designed to calculate the real-time thermal capacity of the power lines.
Seems reasonable so far.
And crucially, they compared the software's estimates against ground truth physical sensors that were actually mounted on the wires.
And the results were brutal.
They were.
The software failed entirely. And to understand why, we have to explain a concept called the limiting span.
Right. So a high-voltage transmission line isn't just one continuous entity behaving the exact same way everywhere. It is a chain made up of hundreds of individual links called spans.
And a span is simply the section of wire suspended between 2 adjacent towers.
Exactly. And the overall capacity of that entire 100-mile transmission line is dictated entirely by its weakest link.
Whichever single span hits its thermal limit first or sags too close to the ground first dictates the maximum power you can push through the whole system.
Yep. That weakest link is the limiting span.
Think of it like a multi-lane highway that suddenly drops down to a single lane around a very tight, dangerous curve.
Good analogy.
It doesn't matter if the rest of the highway has 5 open lanes. The traffic flow is dictated entirely by how many cars can safely navigate that one tight curve.
Right. So the entire job of the SRE software is to identify where that tight curve is, to mathematically predict which specific span of wire will be the limiting span at any given moment based on the weather data.
But the CI study revealed a staggering failure rate. The software chose the completely wrong limiting span 27% of the time.
More than a quarter of the time.
More than a quarter of the time, the supercomputer was looking at the completely wrong part of the wire. How is that even possible? If you have all the weather data, shouldn't the weakest link just be the span that is getting the least amount of wind?
That is exactly the assumption the software designers made. They assumed the limiting span would correlate directly with the lowest perpendicular wind speed.
And it didn't.
No, the physical data from the real-world sensors proved that assumption totally wrong. The study found that 13.5% of the time, the actual limiting span was not the span experiencing the lowest wind.
That defies basic thermodynamics, doesn't it? If wind cools the wire with the least wind should be the hottest. Why wouldn't it be the limiting span?
Because a transmission line's physical state is not dictated solely by the weather in that exact millisecond.
Oh, interesting.
It is deeply affected by its physical history, its metallurgy, and its microtopography. There is a phenomenon called accumulated creep.
Accumulated creep.
Think about it. Over decades of service, as a heavy aluminum wire repeatedly heats up, expands, cools down, and contracts, the metal undergoes metallurgical fatigue. It permanently stretches out.
Like an old rubber band.
Exactly like an old rubber band. So a span that has experienced severe icing in the past, or maybe heavier electrical loads, it might have significantly more accumulated creep than the span right next to it.
So even if two spans are experiencing the exact same 60-degree temperature and the exact same 10-mile-per-hour wind, one span might sag 3 feet lower just because the metal is older and more fatigued.
Precisely. Furthermore, the software cannot accurately model microtopographical changes. Like, it doesn't know if a property owner planted a fast-growing oak tree underneath span number 42, which reduces the safe clearance distance. It doesn't know if the ground under span 88 eroded during a flash flood.
Right.
Software only sees the weather. It is completely blind to the localized physical reality of the wire itself.
And because the software misidentifies the limiting span 27% of the time, it introduces two distinct massive risks into the grid.
It does.
Study breaks these down, and I kind of look at them as the danger risk and the money risk. Let's look at the danger risk first, which happens when the software overrates the line.
Right. So when the software guesses wrong, it often tells the grid operator that the line can safely handle more power than the physical wire can actually tolerate.
And the CIG data showed this happened 12.3% of the time.
Which is incredibly dangerous.
Imagine being that grid operations manager we talked about earlier. You are staring at your dashboard, and this expensive software suite is flashing green, telling you, go ahead, push another 100 megawatts through the line. You have plenty of clearance.
But in reality, the physical wire is already at its limit.
Exactly. If you listen to the software, you are going to push the wire past its thermal threshold. You are going to violate the NESC clearance standards. You are going to risk a massive arc flash.
12.3% of the time, the software is basically handing you a loaded weapon and telling you it's safe.
No grid operator in the world will accept a 12% probability of catastrophic failure. It completely invalidates the software as a safety tool.
It does. But the danger risk is really only half the problem.
Right. The other side of the coin is the money risk, which occurs when the software underrates the line.
Because the software algorithms are designed to fail conservatively, to try and avoid that danger risk we just talked about, they frequently swing way too far in the other direction.
They get overly cautious.
They assume the line is much hotter and sagging much lower than it actually is. The study found that 29.8% of the time, the SRE software underrated the line's true capacity by more than 10%.
Meaning the software is telling the operator the highway is completely jammed, when in reality there are 3 empty lanes.
Exactly. And in the western United States region of the study, so the arid climate with high wind variability, the results were astounding.
What happened there?
The software's worst-case underrating was off by 47%.
47%.
It failed to recognize almost half of the line's actual physical capacity.
Think about what that means for a second. Let's say you have a massive wind farm generating incredibly cheap power. The software looks at the weather, miscalculates the physical sag of the wire, and tells the operator the line is full.
Right.
The operator is forced to order the wind farm to shut down. They leave 47% of the line's capacity completely empty. But the city at the other end of that line still needs electricity.
Yep. The demand doesn't disappear just because the transmission line was artificially capped. The grid operator still has to keep the lights on.
So what do? They have to turn on power plants that are located closer to the city on the other side of the transmission bottleneck.
And those plants are almost always expensive, carbon-heavy natural gas or coal peaker plants.
They're burning expensive fossil fuels to replace the cheap wind energy that they literally threw away because a software algorithm made a bad guess.
It's infuriating.
And who pays for that expensive natural gas? You do, the listener. It shows up directly as a massive spike on your monthly utility bill.
The money risk isn't just an abstract concept for the utility. It is a direct financial penalty on the consumer.
The overarching conclusion from the CIGRI experts is pretty definitive. Without physical ground truth feedback from the line itself, there is absolutely no way to know if your algorithm is accurate.
Software alone cannot remove the human liability.
It merely obscures it behind a wall of code.
Exactly. An operator cannot verify if a sensorless rating is safe, so they must assume it is dangerous.
We are stuck. The static ratings are cripplingly conservative and waste money. The software algorithms are dangerous and wildly inaccurate. Both systems fail because they rely on assumptions, and assumptions trigger human fear.
Right.
If we're going to unlock this phantom grid, we have to stop guessing. We have to measure the absolute physical truth.
And if guessing carries the liability, the only way to eliminate the liability is through empirical, real-time physical measurement.
How do we do that?
This requires a transition to true dynamic line rating, or DLR, powered by physical hardware mounted directly on the conductors.
Our source materials highlight two major players pioneering this physical hardware approach. We've got Heimdall Power with a device they call the Neuron, and Lindsay Systems with their SmartLine TLM monitors.
These are not software models running on a server somewhere. These are robust, physical pieces of technology.
They are highly advanced, autonomous, self-powered sensory units.
And the key engineering feat here is that they are designed to be clamped directly onto energized, high-voltage transmission lines. We are talking about lines carrying up to 765 kilovolts of electricity.
I don't think people realize how insane that is. A 765 kilovolt line will vaporize a bird if it gets too close to a ground path.
Yeah, you can't exactly just climb up a tower with a wrench and bolt a sensor onto a live wire.
No, definitely not.
Historically, installing anything on a transmission line required taking the line out of service, de-energizing it.
But shutting down a major transmission corridor costs the utility a fortune in lost revenue, and it disrupts the grid.
So these companies had to engineer a way to install the sensors while the power is flowing.
The Heimdall Power specifications outline their deployment method, and honestly, it sounds like science fiction. They use autonomous drones to install these sensors.
It is a remarkable application of robotics. The drone flies up to the live wire carrying the sensor.
But how does it not get zapped?
Well, to avoid the drone being destroyed by the massive electromagnetic field surrounding the wire, it utilizes principles similar to a Faraday cage. It equalizes its electrical potential with the high voltage line before making physical contact, preventing an arc flash.
That's incredible.
Then the drone hovers in place, mechanically clamps the spherical neuron sensor onto the braided aluminum conductor, and just flies away. No human beings are required to climb towers, nobody is exposed to high voltage, and the line never has to be shut down.
It's an elegant solution to the deployment problem.
Yeah.
But what is this sensor actually doing once it's clamped onto the wire? What is it measuring that the software couldn't guess?
It is measuring undeniable physical reality. The core technology inside these units is LiDAR light detection and ranging.
Like they use in self-driving cars.
Exactly. The sensor fires a laser pulse downward toward the ground and times exactly how long it takes for the light to reflect back. By doing this continuously, the sensor measures the exact sub-millimeter clearance to ground of the conductor in real time.
So it isn't estimating how far the wire might sag based on the temperature. It is literally measuring the physical distance to the ground with a laser at that exact millisecond.
Exactly. It completely bypasses the complex thermodynamics of accumulated creep and wind cooling and just measures the final result, where is the wire in physical space.
But it also measures the environmental variables.
Oh, yeah. It uses advanced accelerometers and gyroscopes to measure the physical inclination or the specific angle of the conductor where it hangs.
Right.
It measures the ambient cooling effect of the wind, specifically isolating the perpendicular wind speed, which, as we discussed, is the only wind that actively breaks the boundary layer of air around the wire and removes heat.
It measures temperature too.
It measures the exact surface temperature of the aluminum and the real-time electrical current flowing through it.
So let's bring this all the way back to our grid operations manager. We established that they are paralyzed by the fear of liability because they're constantly being asked to make guesses based on bad data. How does clamping a LiDAR sensor onto the wire change that psychological dynamic? How does telemetry remove personal liability from the grid operator's decisions?
It fundamentally changes the nature of the information the operator is relying on. By measuring the exact physical geometry of the wire in real time, LiDAR shifts grid capacity from a fearful conservative assumption to an undeniable telemetry-backed physical fact.
The operator no longer has to guess if the valley wind is cooling the wire or if the 20-year-old aluminum has too much accumulated creep. The instrument simply proves the exact safety margin.
The burden of proof shifts. It moves off the human operator's predictive ability and onto the sensor's optical measurement.
Right.
Think about the NESC regulations. If the law requires an absolute minimum clearance of 25 feet and the SRE software is just guessing that the wire is at 28 feet, the operator is terrified.
Because what if it's wrong?
Exactly. But if the LiDAR sensor is actively firing a laser and definitively proving that the wire is currently sitting at exactly 28.4 feet, the operator knows for an absolute fact that they have 3.4 feet of safe, usable sagging margin remaining.
They can confidently authorize more power to flow through the line without carrying the psychological or legal burden of a guess. The data acts as an impenetrable shield against liability.
Which echoes the philosophy we touched on earlier regarding restorative engineering. Real technology doesn't replace people, it restores them.
The LiDAR sensors absorb the risk so the human beings in the control room can operate with dignity and confidence. We aren't replacing the grid operator with an AI decision maker. We are arming the grid operator with the absolute truth so they can do their job effectively.
It makes complete sense.
We've diagnosed the problem, and we've identified a physical hardware solution that works perfectly. But this brings us to what I think is the most frustrating part of the whole scenario.
Implementation.
Yeah. If this LiDAR technology is proven to work, and it completely removes the liability bottleneck, why hasn't every utility in the world purchased 10,000 of these sensors and clamped them onto every transmission line in existence?
Well, because the energy sector does not operate like the tech sector. You cannot simply walk into a highly regulated, intensely risk-averse utility, drop a glowing LiDAR sensor on the executive's desk, and demand that they radically alter their dispatch protocols by Friday.
They've been operating on static line ratings for nearly a century. It's baked into their regulatory DNA.
The institutional immune system of the utility will violently reject any attempt to rapidly change how they measure safety.
And if you walk into a control room and tell a veteran operator to trust a new laser gadget over the formulas they've used their entire career, they will laugh you out of the building.
Which means the technological solution is useless without an equally sophisticated implementation strategy. This is where the founder's notes provide a masterclass in change management.
And what's the strategy?
They outline a highly specific strategy for introducing this technology to a utility without triggering their institutional fear. They call it the 30-day shadow testing strategy.
This is essentially an undercover operation for grid optimization. I love it. How do we actually execute this shadow test? What is the first step in setting up the initial blind data log?
Step 1 is target acquisition. You do not try to monitor the entire grid at once. You identify a single, historically congested span of transmission line.
So find the worst choke point.
Exactly. The source material references the Nagpur grid in India as a prime example of heavily congested corridors where clean energy is routinely curtailed because the static limits are constantly being hit. You find the worst bottleneck in the system.
Okay, we have our target, a specific line that is constantly forcing the utility to throw away wind power. What's next?
Step 2 is deployment. You bring in the autonomous drone and clamp the LiDAR sensor onto the energized line, ensuring that the utility doesn't have to schedule an outage or put any human workers at risk.
And step 3 is the crucial maneuver, establishing the blind data log.
This is the key. You activate the sensor, but you operate it on a completely non-invasive parallel track for 30 days. You actively prevent the sensor data from interacting with the utility systems.
It is entirely firewalled. The LiDAR data does not touch the utility's energy management system, their EMS. It doesn't connect to their supervisory control and data acquisition or SCADA systems.
Right, it doesn't alter a single operating protocol. For those 30 days, the grid continues to run exactly as it always has, governed by the same conservative static ratings the operators have always used.
This is the genius of the strategy. It is designed entirely around reducing operator fear while introducing sensor-based capacity monitoring.
It is.
You walk into the control room, you look the operations manager in the eye, and you say, "We have installed a sensor on your line, but we are not touching your grid.
We're not changing a thing.
We are not asking you to change a single dispatch decision. We are just passively listening to the wire. Your operational liability remains exactly at zero."
You completely insulate the operators from the risk of the new technology. The sensor just sits up there for a month.
Just measuring.
Every single minute, it is measuring the perpendicular wind, the thermal expansion, the exact laser clearance to the ground. It is calculating exactly how much electrical current that line could have safely carried at any given moment, based on undeniable physical reality.
Meanwhile, down in the control room, the utility is logging how much power they actually allowed to flow through the line based on their static rating.
So the 30 days run out, the shadow test is complete. We now possess a month's worth of ground truth LiDAR data sitting right next to the official dispatch logs from the utility.
What's the next move? How do we calculate the phantom capacity delta?
It's a devastatingly simple mathematical comparison. You take the real-time sensor-derived ampacity, which is the absolute maximum amount of current the line could have safely carried without violating clearance limits, based on the actual cooling and sag measurements for those 30 days.
Let's use some hypothetical numbers to make this concrete for the listener. Let's say the utility's official static plate rating artificially capped the line at 800 amps for the entire month.
Because they assumed it would be 104 degrees with no wind every single day?
Right. But the LiDAR sensor data reveals that for 95% of the month, the weather was actually quite mild. There was a consistent breeze.
So the sensor proves that the line could have safely carried 1,200 amps almost the entire time without ever sagging dangerously close to the ground.
You subtract the static rating from the true physical capacity, 1,200 minus 800.
That difference, that extra 400 amps of safe, usable electrical capacity that was completely ignored by the utility, is the phantom capacity delta?
Okay, we found the phantom capacity. But you can't just walk into the executive boardroom and hand them a single number. Engineers are naturally skeptical.
Oh, very much so.
To ensure the utility trusts the data reliability of the shadow test, you have to present the specific, granular metrics that prove the delta is real. So what specific metrics do we need to track during the test to prove our case?
You must present 4 distinct data sets.
Okay, one.
First, you show the perpendicular wind speed correlation. You have to definitively prove how the wind hitting the wire at a 90-degree angle directly resulted in the cooling of the conductor.
You map the wind spikes directly to the temperature drops on the wire. You show the physics in action.
Second, and most importantly, you present the direct clearance-to-ground measurements. This is the ultimate safety proof.
The laser data.
You show the LiDAR logs proving that even during peak load times, the wire never came within 5 feet of violating the NESC legal distance.
You literally point at the graph and say, look, we could have pushed those extra 400 amps, and the laser proves the wire was still safely elevated.
Third, you track the conductor thermal elongation. You provide a continuous graph of how the wire physically stretched and contracted over the 30-day period.
And fourth,
you must identify the actual limiting span.
tying it directly back to the failures of the SRE software study we talked about. We have to prove to the utility that we aren't just making a sophisticated guess about which part of the wire is the weakest link.
Exactly. You present the data showing that for the first 2 weeks, span A was the limiting span due to a lack of wind in a valley. But for the last 2 weeks, span B became the limiting span because of accumulated creep and high solar radiation.
That's incredibly detailed.
By tracking the true limiting span dynamically, you prove that you are measuring the absolute truth of the entire line, overcoming that 13.5% anomaly where the lowest wind speed doesn't correlate to the weakest link.
Okay, so we've built an undeniable, bulletproof physical case. But as we know, engineers don't sign the checks. And physical data alone doesn't change corporate policy.
Sadly true.
We have to translate this physics lesson for the executive board. We need to discuss how sensor data provides financial evidence of lost revenue from wasted capacity.
This is where it gets real for the boardroom. You take that phantom capacity delta, those 400 extra amps of wasted space, and you calculate how many megawatt hours of electricity could have been pushed through that space.
Then what?
Then you cross-reference those megawatt hours with the wholesale market price of electricity for those specific 30 days. You multiply the wasted energy by the market price.
And suddenly, the conversation shifts entirely. You aren't talking about thermodynamics or thermal elongation anymore. You were holding a ledger of lost revenue.
Exactly.
You look at the CFO and say, by adhering to your static rating and shutting down that wind farm, it cost your company $2 million in lost wholesale electricity sales in just 30 days on this single transmission line.
You have mathematically proven a massive financial loss without having triggered a single ounce of operational liability. The operator in the control room is safe because they didn't alter their dispatch protocols during the test.
But the executive board is now staring at a multi-million-dollar pile of money they left on the table because they were blind.
The founder's notes describe this as the financial gravity of the lost money.
Financial gravity. I like that.
Once the phantom capacity is made financially legible, once you put a dollar sign on the wasted space, the gravity of that lost revenue is so immense that it forces the utilities protocol to change.
The CFO is going to look at the operations manager and demand that they turn the limits up.
And because the LiDAR sensor is now permanently mounted on the wire, acting as an infallible safety net, the operations manager can finally agree to raise the limit without carrying that paralyzing fear of liability.
Which ushers in the final phase of this transformation, the post-liability paradigm. We've proven the money, we've installed the safety net, and we've removed the risk.
Now the fun part.
Let's analyze how removing liability concerns changes the decision-making process for the grid engineers actually running the system.
Well, it triggers a fundamental systemic psychological shift in how the grid is managed. Currently, as we established, grid engineers are forced into a purely defensive posture.
Their entire job revolves around absolute risk avoidance. They spend their shifts basically bracing for impact, terrified of a catastrophic failure.
Their entire mindset is just, don't let the line melt. Please don't let the line melt.
But when you remove that liability by providing undeniable, real-time physical telemetry, those exact same engineers shift from a defensive posture to a proactive, data-driven optimization posture.
Exactly. They are no longer managing ad hoc uprates during emergencies, frantically trying to guess if they can squeeze a few more megawatts through a line during a brutal summer heat wave without sparking a fire.
Right. They can lean into continuous, safe optimization. They can look at their dispatch screens and say, the LiDAR confirms we have 15% more capacity right now on the northern corridor. Let's route that cheap wind power directly into the city.
Grid management evolves from a game of blind survival into a highly sophisticated game of physical efficiency. By giving the grid a physical nervous system, we're finally allowing the humans running it to take a breath.
The human element is restored. Just like the grenade factory, the automation handles the mortal risk, so the human operator can act strategically.
Yes. But the source material leaves us with a fascinating, almost paradoxical twist about what happens after this technology scales globally.
Oh, right. They refer to it as the post-automation choke point.
Yeah, think about it. If this is successful and every transmission line is eventually outfitted with a LiDAR sensor, the physical capacity of the grid becomes entirely legible.
The phantom capacity is completely unlocked everywhere. So what becomes the new bottleneck?
The bottleneck shifts from the physical hardware to the digital orchestration layer. The new choke point becomes real-time transmission capacity forecasting, or TCF.
Okay.
TCF. Once sensors are ubiquitous, utilities will be drowning in massive streams of real-time data showing exactly where the capacity is minute by minute across thousands of miles of wire.
So whoever controls that data.
The firm that can ingest, process, orchestrate, and route that ocean of real-time data will control the arbitrage of peak spot pricing in the energy markets.
It's a massive paradigm shift. The power in the energy sector moves from the companies that own the concrete and copper to the companies that hold the real-time map of the physical capacity.
Exactly. Let's briefly recap the journey we've taken through these sources.
Okay.
We began by exposing the illusion of the full grid, recognizing that we are throwing away massive amounts of clean, renewable energy, not because of the laws of physics, but because of archaic, static, worst-case seasonal assumptions.
We're driving 10 miles an hour every day just in case of a blizzard.
Right. We explored the paralyzing human fear of liability that forces grid operators to stick to those static limits. We saw through the massive Wie Geht study that you cannot just use sensorless software to guess the capacity.
Because the software fundamentally misunderstands the physical history of the wire. It guesses the wrong limiting span 27% of the time, creating both dangerous overrating and highly expensive underrating.
We then examined the restorative solution True Dynamic Line Rating utilizing autonomous LiDAR sensors from companies like Heimdall Power and Lindsay Systems.
By actively measuring the exact laser clearance and physical sag of the wire, they shift grid capacity from a fearful assumption to a telemetry-backed physical fact.
Which removes the personal liability from the human operator.
And we broke down the execution playbook, the 30-day shadow testing strategy. Run a blind data log isolated from the control systems, calculate the phantom capacity delta, and use specific metrics like perpendicular wind correlation to prove the massive financial loss of wasted megawatt hours without altering the dispatch protocols.
You make the lost revenue legible, and the financial gravity forces the institutional change.
Which leaves us with a final unmentioned implication drawn directly from the architecture of the energy sector. Throughout this entire analysis, we've treated the inefficiency of the grid as a problem to be solved.
But structurally, we must ask, who actually benefits from that inefficiency?
The beneficiary of obscurity.
Precisely. If the grid's current capacity remains invisible, obscure, and artificially constrained by these static limits, it creates the overwhelming illusion of a desperate societal need for new infrastructure.
And who is tasked with building that infrastructure? Incumbent transmission monopolies.
Right. Regulated utilities operate on a rate-based model. They don't make their massive profits by simply moving electrons efficiently. They secure their guaranteed financial returns by justifying and executing multi-billion-dollar capital expenditures to build new transmission towers and string new copper wire.
So, a profound conflict of interest emerges. What happens when a $5,000 clamped sensor proves, with mathematical certainty, that those billions of dollars in new infrastructure aren't actually needed for another decade?
What happens when the utility realizes we already have massive phantom capacity sitting right there on the existing wires?
Will the biggest, most powerful players in the energy sector embrace this physical transparency, or will they quietly fight it because it fundamentally threatens their lucrative rate-based business model?
That is the multi-billion-dollar question. Who really profits from the phantom grid remaining a secret? Obscurity is highly profitable for the incumbents. Legibility disrupts the monopoly.
Find the bottlenecks built on human fear and engineer the safety required to unlock them.
We started this conversation picturing a worker in a munitions factory, holding their breath, terrified of the invisible spark that could cause a catastrophe.
And we found the exact same terror sitting in the control rooms of our global power grids, treating a simple aluminum wire like a live grenade because they couldn't see the physical truth of what was happening inside it.
By clamping a lens onto that wire, we aren't just measuring thermodynamics, we are diffusing the bomb. We're finally turning the lights on. It makes you wonder, what other massive critical systems in your life are running on 10-mile-per-hour assumptions simply because the people in charge are too afraid to measure the actual physical risk? Something to think about.